So what's up guys, and welcome to another video solution. This time I'm going to solve problem 47. It's the problem about two inductors, one after the other, which you call inductors connected in series, like in resistors or capacitors. And we have to show actually that we have an equivalent inductance, which is the sum of the inductance of each inductor. And this time we have two inductors right over here. So the one thing we have to do is that when you have an inductor in a circuit, there is a differential potential across this inductor if there is a variation of the current. So the differential potential across each inductor equals the negative of the inductance times the derivative of the current with respect to the time. And this should be a time-dependent current, like an oscillating current. So the voltage across the first inductor, the inductor 1 equals minus the inductance of this inductor times the derivative of the current with respect to the time. And for inductor number 2, we have the negative of L2, the derivative of the current with respect to the time. And you should know that this is the same current. These are the same currents because the current is passing through and the current which is passing through the inductors are connected in series, so the current is the same. And to show this first relation right over here, it's quite easy now because the voltage, this first voltage right over here equals the sum of these two other voltages because they are connected in series. The voltage between these 2 points equals the voltage between this right point until this middle side, and from plus the voltage between this middle side until this voltage from the left side. And using the first relation, we can write the negative of the inductance, and this is actually the equivalent inductance, right? Equivalent inductance, because I'm assuming I have an equivalent inductor of this kind, and the current is passing through it. So this letter is not good. Negative of the equivalent inductance times the derivative of the current with respect to the time equals minus L1 minus L2. Actually we have a current, this current right over here, so we take it out the current, the derivative of the current, and we finally get L1 plus L2. So this is the expression for the equivalent inductance for two inductors connected in series. So now we're going to letter B, which asks us to generalize this expression to any inductors connecting in series. So now that I have cleaned the page, let's continue solving this problem. Let's continue solving letter B. So I write that the total potential, differential potential across all of the inductors equals the sum of the differential potentials across each inductor, this first relation. And the difference potential associated with each inductor equals the negative of the inductance of each inductor times the derivative of the current with respect to the timing. And remember again, it doesn't matter the number of inductors I have, the current is the same. The current passing through each inductor is the same, at least in this case. So one thing that you have to do, that you can do, is actually write this first potential like the negative of the equivalent inductance times the derivative of the current with respect to the time. This equals the summation over I from 1 until n, and let's substitute the V for each inductor equals minus the inductance of each inductor times the derivative of the current with respect to the time. And once we take it out the current, actually the variation of the current, we finally get the equivalent inductance equals the sum of the inductance of each inductor. So this is the right expression to show. Actually, the book don't show this expression, but this is the expression that we have to get. So guys, I hope you have enjoyed this video. I hope if I made some mistake, you can comment below on the video. I also hope that you guys have a good day, and I think I'll see you in the next problem. Bye bye.